Okay, welcome to video 2.3, all about ions, which are charged particles. I noticed that my videos in the last unit started getting a little bit longer, so I'm going to speed things up here. So if it goes too fast, let me know and I'll slow things down as we move through the year. Okay, let's begin by defining atoms. Atoms are one unit of a particular element that are neutral. So when I use the word atom, I want you to also remember that that is neutral. Neutral means the number of positives and the number of negatives are the same. So if I talk about a neutral atom of sodium, we're talking about an atom that has 11 protons, which are positively charged, and 11 electrons, which are negatively charged. You will remember from our drawing board diagrams video that when we draw a board diagram of an atom, we put in the middle the protons. We could also put the neutrons. In this case, I can put 12 neutrons, but we're not going to be talking about them. That's a 12. And we'll look at sodium. Sodium has 11 protons, so if it's a sodium atom, we have 11 protons, which are positive, and 11 electrons. So I went ahead and I drew the 11 electrons in with those red dots. You'll remember that you can find the distribution of those dots on your periodic table in the lower left-hand corner. Down here in the lower left-hand corner, you see a string of numbers. For sodium, it's 2, 8, 1, meaning there's 2 electrons in the first ring. There's 8 electrons in the second ring, that's the second ring, and then 1 electron in the third ring. Okay, back to this slide again. Now, when you have 11 electrons in your rings on the outside and 11 protons on the inside, the element is neutral in charge. Now, the thing is, when we have the valence shell, valence, if you recall, is the outermost ring of electrons. So the sodium atom has 1 valence electron. That sodium atom is not satisfied. It wants to have what we call a full octet. Let's go ahead and write that down. Take a moment and write the definition for octet in your interactive notebook. Okay, so if we look at sodium as a neutral atom, sodium only has 1 electron in its valence shell. That's not going to work because it wants those 8 electrons in its valence shell. So it has a choice. It can either gain 7 more and put those 7 into this outermost shell, or it can lose this 1. It is a heck of a lot easier for sodium to lose 1 valence electron, and when it loses that 1 valence electron, the outermost shell disappears. When it disappears, the sodium now in its outermost shell has the 8 valence electrons. So if I start here and I count 1, 2, 3, 4, 5, 6, 7, 8. So it now has what we call a complete octet. When sodium loses that valence electron, 2 things happen. The number of protons now exceeds, or you have 11 protons and only 10 electrons. When the number of protons exceeds, or is more than the number of electrons, then the overall charge of the atom changes from neutral to a positive charge. So the sodium becomes positively charged. The other thing that happens when you lose an electron is because we lost this outermost ring, the size or the radius of the atom got smaller. Okay? So, what types of atoms tend to do this? They're the atoms that have very few electrons in their valence shell, and those atoms tend to be metals. Metals are the ones that lose electrons and form positive ions. Now, positive ions have a special name, and that's called a cation. Okay? In the next slide, you'll be writing that stuff down, so don't worry right now. Metal ions are usually named by using the name of the parent ion. So, for instance, we would say sodium ion. We use the word ion to tell the person that we're talking to. We are talking about something that has a charge, because ions have charges. They're either positive or negative. The sodium became positive because now it has more protons in its nucleus than it does electrons. I want to take a second here for you to look very carefully at your periodic table. I'm going to zoom in. This side of the periodic table, the left side of the periodic table, have the elements that we consider metals. Now, if you look at metals very carefully, you'll notice that the number of electrons in the valence shell is very low. Lithium has 1, beryllium has 2, and we can, I'm going to slide that up. Wrong thing. Sodium has 1, magnesium has 2, scandium has 2. So you can see that these numbers are very low. Metals, in order to get that full octet, want to lose those outermost electrons. Now, if we take a look at the other side of the periodic table, let's get rid of this word metals so you don't get confused. On this side, you look at the number of valence electrons. 7 valence electrons, 7, 6, 6. They have a lot of valence electrons in their outermost shell. So let's look at fluorine for a second. If fluorine has 7 electrons in its valence shell, it does not want to give up those 7 electrons because it already has 7. It's very close to having 8. So what fluorine will do is it will go out and it will try to grab an electron from somebody else, mainly from the guys on the other side of the periodic table who are trying to lose them. When it gains 1 electron, it now has more electrons than protons. So the number of electrons exceeds the number of protons. Here we can see fluorine, the atom we were just looking at, and if you look at the 7 electrons in the outermost shell, they're labeled or they're colored red. I'll make a red pointer here so we can see. So there's 1, 2, 3, 4, 5, 6, and 7. Then, if fluorine adds 1 electron, okay, now it has a total of 7 electrons, plus the 1 is 8 electrons in its outermost shell. Fluorine had 9 protons. There's 9 protons here, okay, in the nucleus. Let me just show you. Here I'm going to zoom in on fluorine so that you can see, once again, that fluorine has an atomic number of 9, and that means there are 9 protons. So if there are 9 protons, and on the outside we count all of these electrons, including the blue one, which is the one that it gained, now I have 10 electrons out here. Let's see if I have a pen. That's 10 electrons. Okay, I put the little e with the minus sign, meaning electrons with a negatively charged, and we have 9 protons. I'll put a little positive charge there for you. So you have 9 positives and 10 electrons. You have more electrons than you do protons. When you have more negatives than you do positives, you form a negative ion. And the name of the negative ion is called an anion. Anion is a negative ion. When you name a negative ion, in this case it's going to be fluorine, what we do is we take the IDE ending and replace the ending of fluorine, INE, with IDE, and we call it a fluoride ion. So it would be a fluoride ion instead of just fluorine ion. That's how we name the negative ions. Okay, in case we didn't get it yet into our notebooks, it's very important that you know the definition of an ion. An ion is a charged particle that forms when an atom that is neutral gains or loses electrons. And you also should know that an atom is going to gain or lose these electrons in order to complete its outermost valence shell. Remember that the atom wants a complete octet. Octet meaning 8 valence electrons, except if it is hydrogen or helium. And in that case, they only want 2 electrons because hydrogen and helium only have 1 valence shell or 1 shell. And that first energy level can only hold a maximum of 2 electrons. So take a moment and write these things down. In your notebook, I also want you to write the definition of an anion, which can stand for a negative ion. Oh, that's black. We don't want to write in black. So we'll have A, the N is the negative, and then we have ion. So a negative ion is an anion. They form when an atom gains electrons. The things that mostly gain electrons are the nonmetals, or the elements that are on the right side of the periodic table. They become negative ions. That's why they're anions. Their radius gets bigger because I am gaining electrons, and the electrons are making the shells expand. And my electron configuration will change to that of a noble gas electron configuration. Let me show you what I mean by that. Okay, so I'm going to draw fluorine. Fluorine has an atomic number of 9. When you look at your periodic table, you're going to see that fluorine has an electron configuration of 2-7. 2 electrons in its first ring, 7 electrons in its second ring. That means it has 7 valence electrons. Okay, so these are the valence. It wants to get 8 electrons in its valence shell. So what it does is it absorbs or gains 1 electron, and its electron configuration becomes 2-8. 2-8 makes fluorine have a -1 charge. It has more electrons than it does protons now. So here's my ion. Here's my atom. Okay, the ion has 1 more electron than the atom does. Well, because it has 1 more electron, its electron configuration changed. It changed from 2-7 to 2-8. Well, that 2-8 electron configuration matches an electron configuration of something called a noble gas. The noble gases on the periodic table are over here in the very last column. Noble gases have full valence shells, including helium, which has a full valence shell, but it only has 1 shell. So that first shell, remember, can only hold a maximum of 2 electrons. So because it is 2 electrons there, it is full. The others, if you look very carefully, let me zoom in. Maybe I can zoom in. Let's see. You'll see that they all have 8 valence electrons. 8, 8, 8. That means their valence shell is full. When fluorine gains that 1 electron, its electron configuration becomes just like neon's electron configuration. It does not, however, mean that fluorine becomes neon. Fluorine is just becoming a fluoride ion. Neon remains neon because it has 10 protons. Fluorine remains fluorine because it has 9 protons. Fluorine does not change into neon. What happens is its electron configuration becomes that like neon's. If I zoom in and show you sodium, sodium was a metal. Metals tend to lose their valence electron. So sodium would lose this valence electron, this one right here, and would also have an electron configuration of 2-8. When it does that, it will also become an electron configuration that matches neon. Okay, so we have all of the information about anions. Let's get into our notes, the definition about cations. Cations are positively charged ions. I tend to tell my students that you can remember cations are positive because if you write the word cation with a big plus in the middle, that plus will remind you that it is a positively charged ion. So they lose electrons. When they lose their electrons, they have more protons than electrons, and they become positive ions. The radius becomes smaller because you tend to lose that valence shell, so your next shell in becomes your valence. Your radius becomes smaller because you lose the valence shell, and your electron configuration changes to a noble gas electron configuration, just like I showed you on the last slide. Okay, just to recap and make sure that everybody is perfectly clear on what an ion is. Ions are atoms that have gained or lost electrons and are charged, and we can predict what that atom is going to do based on its position on the periodic table. Metals that are on the left-hand side of the periodic table tend to lose or give up their electrons and become cations, and non-metals on the right-hand side tend to gain their electrons and become anions, a negative ion. Take this moment and write that stuff into your notebook. Okay, the very last thing that I want to talk about in this video is something called a polyatomic ion. Poly means many. So this little prefix here means many atoms that are acting like ions. And once again, ions are charged particles. So we've got these groups of atoms, many atoms, that are acting like ions. I want you to take a moment and write this in your interactive notebook. Polyatomic ions are groups of atoms that stick together and have either a positive or negative charge. We find these polyatomic ions. We don't have to memorize them, thank goodness. You will have to if you take AP Chem, but we don't have to memorize them. They're located on Table E for us, and there are 7 of them that I want you to A, write into your notebook, and B, commit to memory, because we're going to see them a lot this year. So here is our Table E, and you can see it says on the top, select polyatomic ions. Poly again means many. So let's take a look at one that you're going to have to keep a close eye on because it shows up quite a bit. We'll start with this one right here, this CO3-2. When we look at this particular polyatomic, you've got 2 elements that are joined together, that are bonded together. I shouldn't have circled that because now it's a big red circle in the middle of my thing. Here, let's get rid of that. I'm getting better at this. Okay, so we've got CO3, -2. We've got 2 elements. We've got a carbon and we've got oxygen. Notice that because there's more than one element, we call this polyatomic. And also, right here, you have a charge, and the charge is -2. So that means there are 2 more electrons than there are protons in here. This polyatomic ion happens to be made of 1 carbon and 3 oxygens. So this, let's talk about some vocabulary here since we have a second. The carbon has no number to the lower right of it. That when it has no number, we're going to assume it's a 1, so that means there's 1 carbon. And this guy, this oxygen, has a 3 to the lower right. These numbers are called subscripts. So oxygen has a subscript of 3. That means there are 3 oxygens. So in this case, we basically have 1 carbon and 3 oxygens. Oxygen, oxygen, oxygen. And together, they have a specific number of protons. We're not going to get into it. But they have 2 more electrons than they should. And because of that, they have more electrons than protons, and they have a charge of -2. Do not get thrown off by the fact that the negative is written after the 2. It really doesn't matter for our level of chemistry at where you write the positive or the negative. Sometimes they'll write it after, sometimes they'll write it before. So don't get thrown off by that. So you should know these 7 polyatomic ions and commit them to memory because you're going to see them quite frequently. You're going to see carbonate, you're going to see acetate, you're going to see ammonium, you are going to see hydroxide, you're going to see sulfate, you're going to see nitrate, I'm missing one, where is it? Oh, here it is. And you're going to see phosphate. So those are the 7 that I want you to pause the tape right now. Make sure that you have them in your notebook so that you know what they are. So if I ever said to you ammonium, you would say, oh, ammonium, that's a polyatomic ion. If I said acetate, you would say, oh, that's a polyatomic ion, and you would know exactly where to look for those. So go ahead and pause me and write those down. Okay, let's just recap before the video gets too long. We went over what an ion is. It's a charged particle. You should be familiar with Table E and polyatomic ions. You should know the vocabulary cation, anion. When you're asked what happens to the electron configuration of an atom when it turns into an ion, you should be able to write that down. You should also be able to talk about what happens to the radius or the size of an atom when it turns into an ion. I hope this video helped. If there's any questions, see me in class. Until next time.